Right, so, can I make that brighter? That's better. Right, in case you've never met me, I'm David, and I'm the coordinator of the Math Learning Centre. And for the past couple of years, I've been doing sort of revision seminars during Spot Week in the hope that it helps people. I presume it does. People keep coming, though it's a new group of students, so it doesn't really make sense to say people keep coming. What I've done this semester is I put last year's in my uni for you, and I've now put them all on one page on the Maths Learning Centre website. It doesn't have a link to it directly from the Maths Learning Centre website front page, but there is a link to it in my uni now. So all of the seminars that I've done are all in one place now if you want to look for them. So over the last week I've been asking people what they would like me to do, and several people said Eigen things, and then a few people said random other stuff. So today I'm going to spend the first 40 minutes or so talking about Eigen stuff, and then the next hour or so taking requests. If you need to leave, that's fine, but I will record all of it, okay? So, and it will go up probably tomorrow morning when the video arrives in my inbox. So, I should say it's not technically my job to teach you maths. I'm the Maths Learning Centre. I'm supposed to teach you how to learn maths. But unavoidably, I have to teach you some along the way if I'm going to teach you how to learn it. Technically, that's your lecturer's job. So I need to have some sort of different spin on this so as not to offend your lecturers, right? Because they'll think that, why is David teaching it again when I did a perfectly good job? So what I'm doing now is to try and help you organise what you've already seen in this topic. And hopefully the advice I give will be useful for other areas, because I can't do the whole of Maths 1A again, because you already did that. So I want to help you organise this topic so you can keep it all in your head at once and be able to solve problems that you've never seen before based on the stuff that you have seen so far. So let's just start. The most important thing about Eigen things is the definition. And this is the thing that most people actually forget. And when I ask them what's the definition of an eigenvalue, they won't be able to tell me. And this is the most important thing, and therefore the most important thing to remember. So the definition goes... So for a square matrix, we'll call it A. If AV is lambda V, is that too bright? Yes, it is. For some number lambda and some vector v, which is not the zero vector, then v is an eigenvector of the matrix A, and lambda is an eigenvalue of A. That's the definition of both eigenvalue and eigenvector. All in one go. If you ever ask for what's the definition of just an eigenvector, then it's a vector such that AV is lambda V for some lambda. An eigenvalue is it's a number such that AV is lambda V for some V. Okay? That's the definition. And it is possible to prove all sorts of things from the definition. And if you're ever asked to prove stuff about eigen things, that's usually where you start. Okay? With that definition. So I'm going to show you something. Using just that, I can do a proof that goes like this. If lambda is an eigen, I'm just going to shorten it to E value of A, prove that lambda squared is an eigenvalue of A squared. It's a classic, that's not a question mark, that's a squared. It's a classic assignment question, and it's very short, so who knows, it could be in an exam. So the way to do that is to use the definition. So since lambda is an eigenvalue, AV equals lambda V for some V not equal to 0. Okay, so the vector isn't allowed to be 0, though the lambda itself is allowed to be 0, it's just that the V isn't. Yep?
I think that's a bit off because it's hard to read it.
Yeah, it's quite blurry.
It is quite blurry. It went past the good one, didn't it? Is that better? Cool. I've used the Flenchy every day for the past week, and the document camera has been different every day. Sometimes it's blue for no good reason. Sometimes the light isn't good. I'm really not sure what's going on. Okay, so AV is lambda V for some V not equal to 0. And thank you. The note that you can interrupt me at any point if there's something I've said that either doesn't make sense or is just plain wrong, or you can't see what I'm doing. Please do that. Okay, so AV is lambda V for some V not equal to 0, and we want to show that lambda squared is an eigenvalue of A squared, so we should get A squared into this equation somewhere. So the only way I know to get A squared in is to multiply by A. That'll get an A squared into the equation, because if I can make A squared times something equals lambda squared times something, that will make it an eigenvalue. So this is A squared V, which is a good start. That's I can bring lambdas out the front because it's just a number. But we already said that AV was equal to lambda V, so we can sub that in. And that's lambda squared V. And that's it. A squared V is lambda squared V. So the matrix A squared has this number to go with it. So therefore, lambda squared is an eigenvalue of A squared. And that's pretty much all there is to it. It's a very short proof. But what I did is I used the definition of eigenvalue twice. Okay, once for A and once for A squared. You don't need to know anything about what eigenvalues do at all in order to do that proof. Okay? So, as I've said to many people before, for a mathematician the definition is really all there is. They often don't even think about what it means at all. They just think, well, what does it mean? It means the definition. Okay, so your lecturer will expect you to be able to do that sort of thing without knowing anything about the rest of the course about eigenvalues. So that's the definition. So what we want to do after that is actually know, well, what does it mean? Because that's really important. So there's two things that are going to be going on here in the topic of eigen stuff. There's how to find eigenvalues and eigenvectors, which is one area, and then there's information about them that might be useful. And sometimes you'll get questions in exams that say, find the eigenvalues and eigenvectors, and sometimes you'll get them to give you some small bits of information, and from that you have to figure out what they are. But you won't be told what the matrix actually is, okay? Because there are various bits of information that go together that are related to each other that you can use to solve problems. So we're going to need to do both. So firstly, how to find them is the... So we're going to find them. And most people are okay with this traditionally when I talk to them. You get your matrix A and you do this. You write this equation down. You get lambda I take A, or depending on your lecturer, A take lambda I. Doesn't matter either way. And you set it equal to 0 and you solve that equation. So just this part here, without the equal to 0, is called the characteristic polynomial. And this part here with the equal sign, that's the characteristic equation. That's just terminology. A polynomial doesn't have an equal sign, but an equation does. That's pretty much all there is to it. And so either you're going to solve it to get lambda equals blah, 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 or you're going to factorize the characteristic polynomial, or probably both, and that will tell you what the eigenvalues are. Okay, that finds the eigenvalues. Once you've got them, so this gives like lambda equals, and you'll have all these answers here. And then after you've got those answers, you'll sub them back into this original thing, but without the determinant, just with the original matrix. So using each answer, we'll solve this equation. Technically, we're solving this. Lambda I take A times x equals 0. That's technically what we're doing, but you won't write it down that way. What you'll write down is you'll get the matrix lambda I take A, and you'll do row operations. And you'll find that you'll get a free variable definitely, and that free variable will help you tell what the eigenvectors are. Okay, that's the process, and I will do a proper example, but I need to describe how the process works. It's very important for you when you get told a process in the lectures to find a way of remembering how it works and writing it down for yourself so it will stick better. Right, that's how to find eigenvalues and eigenvectors. But before I move on, while I'm at it, I should talk about what an eigenspace is. So I'm just going to put a page in between here and here. Okay, so this is a definition. I don't know if this is a definition in your notes, but it works perfectly well and your lecturer will accept this. The eigenspace for a number lambda is E sub lambda, E for eigenspace. It's the set of all the vectors x such that AX is lambda x. That's what it is. It's a solution to that equation, which is all eigenvectors for lambda plus the zero vector as well. Okay, that's what it is. So normally the zero vector is not included as an eigenvector because A times 0 is lambda times 0 no matter what lambda is. A times 0 is 3 times 0 is 4 times 0 is 5 times 0. So if you're going to allow 0 to be an eigenvector, then any number could be an eigenvalue because any number could go in that equation to make it work. So you don't usually let 0 be an eigenvector. But if you want to make a space, it has to include the 0 vector, so you put it back. Okay, so you get all the eigenvectors and the 0 vector as well, and that produces an eigenspace. Okay? That's the definition of an eigenspace. So back here, when we're solving this equation here, lambda I take A times x is 0, that's just a rearranged version of the equation that I wrote here. So what you're actually doing in that spot is finding the eigenspace, because the 0 vector will be included in your solutions when you do that. So technically you're supposed to throw it out once you get to the end. Okay. So it finds not just the eigenvectors, but also the eigenspaces, which is why I needed to mention eigenspace at the point I did. Okay, so this is the process of finding them, and it does not require us to understand what they mean, though I will talk about that shortly. But I'll do an example of finding them. So I'm going to do a couple of examples, and hopefully I'll illustrate some of the things that I'm talking about here. So you might be asked to say, verify verify that 1, 1, 0 is an eigenvector of this matrix A, which is 2, 3, 1, 3, 2, 1, 0, 0, 5. You do not have to go through that whole process that I just said in order to answer this question, because the word verify just means check. establish the truth of. That's what verify literally means in English. And in order to know that this is an eigenvector, all I need to know is whether A times that comes out to number times that, because that's what an eigenvector is. So I do not have to go through that whole lambda I take A thing in order to show this. All I have to do is this. So 2 plus 3 plus 0 is 5. 3 plus 2 plus 0 is 5. So when I multiply that matrix by that vector, I got 1, 1, 0, and that gives me 5, 5, 0. And that's 5 times my original vector. So it's an eigenvector. That's all there is to it. So it is an eigenvector with eigenvalue 5. So that's my V, and that's my lambda. Okay, so if you're ever asked to verify, that's all you need to do. You don't have to do anything else after that. But if you're asked to find the eigenvectors, well, that's a whole different story. Where A is equal to that same matrix. Okay, so if I was asked to find the eigenvectors and eigenvalues of that, then I would have to go through that whole process. So first, I can't find eigenvectors unless I find eigenvalues first. So first I'm going to have to do the lambda I take A thing. The determinant of lambda I take A. So let's see. We take A, just giving myself some space here. Like that. And then we add lambda I on top of that. And lambda I is the same as I, it just has lambdas down the diagonal instead, so we can put our lambdas on the diagonal. If I do it this way, it prevents me forgetting to do all the minus signs in the correct spots. If I do the minuses first and then the lambdas, often if you do the lambdas first, you'll forget to put minuses on all of these ones at the edges and you'll just get the answer wrong. So you need to do something that will prevent you from getting the wrong answer. And then I will need to actually just find that determinant. So a 3 by 3 determinant, I can go along any row or column, and I'm going to pick this last row because it's got a heap of zeros in it. It's going to make my job easier. So let's see, plus, minus, plus. So it's going to be plus 0 times another determinant, minus 0 times another determinant, plus lambda minus 5 times this smaller determinant here. Like that. So I've got lambda minus 5 and lambda minus 2 squared minus 3 squared, which is that. So far that's the characteristic polynomial. If you're asked specifically for the characteristic polynomial, you would normally expand it out. But since I don't want the polynomial, I only want the eigenvalues, there's no point expanding it out because I've already factorized it. See, there's the 5 that I already have. Okay, so I need to factorize this other bit. I could expand it out and that would be fine. Expand it out and then use some sort of quadratic to try and factorize that quadratic. But it's already the difference of 2 squares, so I can actually go lambda take 2 plus 3 and lambda take 2 minus 3. Does a perfectly good job. Because if this was like x squared minus 9, it would be x plus 3x minus 3. I could factorize it like that using the difference of 2 squares. And so I've got lambda minus 5, lambda plus 1, and lambda minus 5 again. Yay! So I have 3 eigenvalues, and there ought to be 3 because it's a 3 by 3 matrix. 2 of them are 5 and the other one is 1. So the eigenvalues are Oh, other one is minus 1. Okay? So I don't even need to actually set that equal to 0 at this point, but technically that's what I've done. Make that equal to 0, which tells me that I've got 5 and minus 1. Okay? The same as if you were solving any equation like that. So while I'm at it, this means that 5 has multiplicity 2. Now the word multiplicity refers to how many times it appears in this list. Okay? Okay, so let's see. Now that I have them, I can find the eigenvalues, eigenvectors. So for lambda equals 5, I do my 5i minus a. So that means that back here, I can sub 5 in for lambda in that equation there. So I've got 5 minus 2 is 3. 5 minus 2 is 3. And 0, 0, 0. Because 5 minus 5 is 0. And I would do row operations until I got to the stage where I could actually solve that equation. So you are allowed to actually cheat a little bit here, because unless they tell you to show your row operations, you can do it in whichever way you think is best. Okay? Personally, it takes me longer to enter matrices into my calculator than to do it by hand, but if you're speedy at your calculator, go for it. Okay? Me personally, normally you'd be putting a 1 here and a 0 here, and you'd be heading down that road, but yeah, I'll do it. I've already got, I can make the 0 before making the 1. Like that. Oops, there's supposed to be a row of zeros. And divide that 1 by 3. Looks like I can go here eventually if I'm careful. And that will get me. Okay, so I can actually skip my row operations if I'm very clever. So what I've actually done there is I've divided row 1 by 3. I've divided row 2 by minus 2. And I've gone row 1 equals row 1 minus the appropriate multiple of row 2, whatever it is, I don't even care. So that's produced this. And you'll see that here is the first column of the identity and here is the second column of the identity. So the other column is a free variable. So this one can be t. And I get that z is 0 and y is, and x is y, which is also t. All right? I'm able to do that by hand, but if you do that straight up, but if it makes more sense to you to do this, let y be equal to t, then z is equal to 0 and x minus t is 0 and therefore x is equal to t, then go for it. It's better to take longer and get it right than to do it quickly and get it wrong. Okay? Because in the end you'll still have to check it, so you might as well take a little longer and get it right. So this, I can bring the t out the front. And that is the list of all the eigenvectors that go with 5. And also includes the 0 vector as well. So I'll fix that in a minute. And for lambda equals minus 1. I sub that into the original matrix, which is here. So minus 1 minus 3 is minus 3. Sorry, minus 1 minus 2. Like that. And already those two rows are equal to each other, so I'm going to get this decent row of zeros eventually. I can divide this one by minus 6. can wipe out them, therefore. I'm going to get this eventually if I actually do it properly. Okay, so I subtracted row 2 from row 1. I divided this one by -6, and I subtracted it, added it onto there, and then divided that one by -3, and it all came out to this. So again, I've got 2 identity matrix columns, and this one's free this time. So I can make y equals t, x will be minus t, and z again will be 0. And so I've got t minus t, t 0, which is t times -1, 1, 0. Right, and if you're ever doing this in exam, it is important to say at the very end what your final answer is, because you were asked specifically what it was. So we can say that the eigenvalues are lambda equals 5, 5, and -1. The eigenvectors for lambda equals 5 are t minus 1, 1, 0 for t not equal to 0. Because technically if t is 0, it's not an eigenvector. And the eigenvectors... But if you're asked for the eigenspace, that E5 is equal to all of those. Okay? So the difference between saying what are the eigenvectors and what's the eigenspace is the eigenvectors doesn't need curly brackets. You can just say it like this, and you have to explicitly specify that t isn't 0. But if you're asked for an eigenspace, then you just whack some curly brackets around it, and that makes an eigenspace. You could also write this like this if you wanted. The span of -1, 1, 0. You wouldn't have to write this if you didn't want. Just take the part without the t and whack a span around it. And if you've got 2 vectors, you just put them both in the span. And that means that this here is the basis for the eigenspace. Just while you're at it. And finally, the eigenvectors for lambda equals -1. Oh, crap. I was copying the lambda equals -1 here, but it's actually from the previous page. Yeah. For t equals 0. And E minus 1 is the span of -1, 1, 0. Okay, so I've found the eigenvalues, the eigenvectors, and the eigenspaces, and that's how to do each of them. And remember, you don't have to do all 3 of them if you haven't been asked to. If all you've been asked to do is find the eigenvalues, then you would stop way back here and you wouldn't do anything else. But if you've been asked to find the eigenvectors, you do have to go all the way here, but technically you don't have to write down what the eigenspace is. Okay? So just be careful of what you've been asked to do. Any questions before I move on that? Cool. All right. That's finding eigen things. Let's make sure I've got it all in the right order. So let me just talk a little bit about what eigen stuff means, because most people don't understand, and it's actually quite confusing, because the eigen things are information about a matrix. So what does it mean? So the first thing that it means doesn't really mean anything, but it's just like eigenvectors and eigenvalues are information about the matrix. Okay, that's what they mean. Okay, it's just more information about the matrix. You know how to find a determinant, you know how to find a transpose. It's just something else that you can do to matrices. So you get the matrix and you can pull out this information of the eigenvector and the eigenvalue. It just so happens that it's actually really, really useful information about a matrix because it's related to so much other stuff. So it's useful information. But it's only useful because of how it's related to things. That's one meaning for it. You can just think of it that way. I can just get a matrix and I've got this magic process that produces an eigenvalues. Okay? The other thing that it is it actually is a way of thinking about the matrix as a transformation. So every matrix can be used to put as a function that you put vectors in and it spits vectors out. Okay, so think of your matrix as a transformation. So what you can do is you can create this function that when you multiply, you get a vector, and you want a vector as your answer, and you just multiply it by a matrix and it tells you what the vector is. So as an example, we can go 1, 0, 2, 5, and we could have a before picture and an after picture. And what you can do is you can multiply vectors by that matrix and see what they come out to. So we might have the vector 0, 0. So if you go A times 0, 0, you'll produce 0, 0 again, which is not particularly helpful, but it's worth noting. If you put 1, 0 in, which is this dot here, that's the point 1, 0, and you multiply it by the matrix, let's just see. We'll get 1, 2. So that point there becomes here, 1, 2. And if I put in, say, 0, 1, which would be this one here, I will get 0, 5. So I will get, just need to make a bit more space. I will get this. Okay, 0, 5. And any vector I could put in, I could get a vector out. So just as a final example, I could put in, I wonder what the other eigenvalue is, 1. No clue. Okay. I could put in, say, minus 1, I could put in maybe 3 minus 1, just to pick a random one. And when I do that, I'll get 3, 6. I'll get 3 plus 1. So I might put in, running out of decent colours, light pink, eh? So 3 minus 1 is here, and the answer will be at 3 plus 1, which is here. Okay, so every point will be moved to a new point. But notice that this point here ended up on the same line through the origin that it was before. That's what eigenvectors are. Okay, when you move them via the matrix, they end up on the same line through the origin that they were in before. So what's going to happen with this matrix is that we're going to end up with every point that is on this line, when I do the matrix to it, it will end up somewhere else on that line. And so if I take the whole line and do the matrix on every point, nothing will happen to the line as a whole. Every point within it will stretch a little further out, but the line as a whole won't change. That's an eigenspace. An eigenspace is a line or a plane or something like that through the origin that as a whole doesn't move when you do the matrix on its points. All the points within it will move somewhere, but the plane as a whole doesn't change. Okay? That's what an eigenspace is about. And eigenvectors remain on the same line through the origin. There is one exception to that. The whole eigenspace could be wiped out and turned into the zero vector. That's one exception. So eigenspaces either don't change or they just become the zero vector. Okay, that's what they are. And there would have been an assignment question that had like an oval and you had to figure out what the eigenvalues of the matrix were, which is always really annoying. But the idea is that if you can find a point that didn't move or that stayed in the same direction on the same line, it must be an eigenvector. So another example. So if you had like a circle, that's supposed to be a circle. And when you did the matrix on the points on that circle, you produced a new shape. What will happen is that the ones that were eigen values or eigenvectors will be stretched in the direction they are, and everything will follow along. So you could have something maybe like this, like that, and maybe that's the point 2, 2, and that's the point minus 1, no, 1, minus 1. So what's happened is that, you see, this point here has been stretched outwards to produce that point there, but it's still in the same direction as it was before. And this point here has been stretched out inwards, outwards to produce that point there. And all you have to do is figure out how long, what multiplier to use to make one into the other. So far we've already got the eigenvectors. So 1, 1, anything in that direction is an eigenvector, and anything in this direction is an eigenvector as well, and they'll do perfectly well. Okay, you can use that whole line. Okay. And we want to know how they've been changed. I believe that's 1 on root 2, 1 on root 2. So what's happened is it's been multiplied by root 2 to get to there. So root 2 is its eigenvalue. And that was 1 on root 2, 1. So this is 2 root 2 as the other eigenvalue. Okay? Because we need to know what that point is. It's 45 degrees. You can use sine and cos to figure out what it is. And then you need to know how much longer it's been made. I have no clue if someone is going to ask you a question like this. It's just something that they do in assignments. Usually they're less way out in exams than they are in assignments. So knowing that in an assignment, they know you've got a week to think about it. So in an exam, they know you've got less than an hour to think about each half of the exam. So they won't do something crazy like this. But you never know. I have no clue what's in your exam, not having seen it. Because I'm not part of the School of Maths, so I have no influence on your exam at all. Much as I wish I would like, wish I could. That would make my life so much easier. That's what eigenvectors and eigenvalues and eigenspaces mean. Okay, so I said there was the other half of eigen things is the information about them. So information about eigen stuff. Right, so we've been told we know how to find them. We can chuck them into this lambda I take A thing. We can figure out that determinant. We can then put it into row operations and figure out the vectors that go with them. That's great. But there's more information about it. And sometimes even if you're not told what the matrix is, you should be able to figure out what some of its eigenvalues are. So the first piece of information is an n by n matrix has n eigenvalues. Now, that's not technically true, of course, because the other one I had before was a 3 by 3 but only had 2. We count them as many times as they appear in the characteristic polynomial. Okay? So we say according to multiplicity. And multiplicity means that if it appears more than once as in one of those factors in the characteristic polynomial, then you count it twice in the list. Okay? So you expect a 3 by 3 matrix to have 3, and a 2 by 2 matrix to have 2, and a 7 by 7 matrix to have 7. Okay? That's fact number 1. Now, I'm just listing them as dot points, but they are theorems somewhere in your notes. All right? The next one is that if you add up the eigenvalues, you'll get the same answer as if you add up the diagonal. Sum of eigenvalues equals trace of A, which is the sum of the diagonal. Okay? So it's not to say that the eigenvalues are definitely on the diagonal. It just means that if you add up the diagonal of the matrix and you add up the eigenvalues, you'll get the same answer. All right, and you have to include them in the list as many times as they are. So as an example, that matrix that I had before, just to prove that it's true, it doesn't prove it, but just to illustrate, the eigenvalues of this matrix were 5 and 5 and minus 1. And you'll see that the sum of these is 2 plus 2 plus 5, which is 9. And if you add 5 plus 5 minus 1, you also get 9. That's pretty much the idea. Okay? And the other one is that the determinant, well, the product of the eigenvalues, if you multiply them all together, the product of the eigenvalues is the determinant of A. So that wicked process of finding determinants, if you know the eigenvalues, you can shortcut that and just find the eigenvalues. All right? Now, what other information is there? Okay, there's some more information which says that the dimension of the eigenspace is less than or equal to the multiplicity of the eigenvalue. So remember, dimension is the number of basis vectors. So the number of basis vectors you get is less than or equal to the multiplicity of the eigenvalue. So you'll notice in the other one, it had multiplicity 2, but I only got one eigenvector, one basis vector for my eigenspace. It's possible for that to happen, but the maximum I could possibly have gotten was 2. I could never get 3 if the multiplicity is only 2. Okay, so that's useful as well. You can see I'm doing this all off the top of my head, so please, it's your responsibility to check if I've missed anything. That's about it, I think, except things about diagonalizability. Well, did you want to say something? Was it you?
Does the product and the sum relate to the characteristic equation?
They do, yes, and this is another fact which is also useful. So if you've got the characteristic polynomial, which will have a lambda to the n to begin with, and then it will have stuff okay, so you'll write it out. If you do it as lambda I take a, you'll get a lambda to the n at the beginning, and you'll get some coefficient here next to the lambda to the n minus 1, and you'll get some constant term on the end. Let's see if I've got this right. This is minus 1 to the n times the determinant. No, it's not. This is minus 1 to the n times the product of the eigenvalues. Okay? Which means it's minus 1 to the n times the determinant as well. All right? And this number here is minus the sum of the eigenvalues. Now, most people don't notice that, but it's actually, in order to prove that the sum of the eigenvalues is equal to the trace, you have to use this fact here. And it would have been somewhere in the lectures. So when you expand it out, I'll show you in an example in a second. When you expand out the characteristic polynomial, the trace will be, well, minus the trace will be here, and plus or minus the determinant will be here. But it'll be plus the determinant if it's an even by even matrix, and minus the determinant if it's odd by odd. So just in brackets, it will be the product if n is even, and minus the product if n is odd. So this one's always minus. Okay, and the final piece of information about a matrix and its eigenvalues is the Cayley-Hamilton theorem. So the Cayley-Hamilton theorem says that a matrix satisfies its own characteristic equation. So if A is inserted into its characteristic polynomial instead of lambda, then the result is the zero matrix. That's a way of saying it in words. The other way is to say, i.e., if the characteristic polynomial is what I said before, a to the n plus cn minus 1, a to the n minus 1, plus blah, 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 plus c0i, because you can't just have plus c0 on the end, it has to be a matrix, so it's c0 times I, that will be the zero matrix. That's the Cayley-Hamilton theorem, which is like truly magic. And the proof of it is utterly awesome and uses adjoints, which is one of the purposes of teaching you adjoints, but the proof of the Cayley-Hamilton theorem over time has been removed from the course, but the adjoints are still in. So there you go. It really is the most awesomely wonderful proof. It's a magic trick. So nothing up my sleeve and everything disappears and cancels out and becomes zero. But I'm not going to show you because you don't need to know. But if you're ever interested, ask me and I will be extremely excited. So eigenvalues are the coolest thing to me. They became cool to me when I had to lecture it. And I didn't understand them until I had to teach it, which usually happens. So that's the final piece of information you might want to know, other than something about diagonalizability. So I'm going to add that to that list, this list in a second. But I want to do some examples. So let's do some examples. So a matrix, a 4x4 matrix has one. Let me just think this through. All right, I'm going to be really crazy to you. So a 4x4 matrix has the number I, and the complex number I, as an eigenvalue. It has trace 2 and determinant 5. Find all the eigenvalues of A. Okay? Yay. Yes. So, well, let's just say, it's the real matrix A. So, a 4x4 real matrix has I as its eigenvalue. So if it's a real matrix, all of its entries are real, the only possible way to get a complex number is that when you factorize that equation, you'll get a complex number. And the only way for that to happen is for the conjugate pair to be in there as well. So complex eigenvalues occur in conjugate pairs, which might be something that's worth adding to the list of information about eigenvalues that I put up before. So minus I is also an eigenvalue. Okay. And we know that it has 4 eigenvalues in total. Okay, so let the other 2 be lambda 3 and lambda 4. Okay, because it's a 4x4 matrix, so it ought to have 4. We've already got I and minus I, and that leaves me with lambda 3 and lambda 4. Okay, and then because of the trace and the determinant, we know that I plus minus I plus lambda 3 plus lambda 4 is 2. And I times minus I times lambda 3 times lambda 4 is equal to 5. Cool. So we've got 2 equations and 2 unknowns. So let's see, that means we've got lambda 3 plus lambda 4 is 2, and lambda 3 times lambda 4 is 5. Don't like my chances of finding anything useful out of that, but anyway. And I would solve those 2 equations. The quickest way is probably to... Actually, the quickest way is this. You could rearrange that one and sub it into here, or you could rearrange this one and sub it into there, or alternatively you could multiply this one by lambda 3. 1 times lambda 3 gives me lambda 3 squared plus lambda 3 lambda 4 is equal to 2 lambda 3. But according to that equation, lambda 3 lambda 4 is 5. And now we have this, we have this awesome quadratic equation, or possibly awful, depending on your perspective. And more doesn't look likely. I'll have to use the quadratic equation to solve that, unfortunately. Your lecturers will be nicer to you than that, but I made this up on the spot, so yeah. So we get lambda 3 is minus b plus or minus b squared minus 4ac. Oh, yikes. So minus 20 over 2a. Wow. So that's negative, gosh, 2 plus or minus root negative 16 over. So 2 plus or minus 4i, which is 1 plus or minus 2i. Sorry about that. That really wasn't a very good example. But that's okay. So all the eigenvalues are now I minus I, 1 plus 2i, and 1 minus 2i. Now I know that I only just figured out lambda 3, but if you look at those original equations, lambda 3 and lambda 4 are the same in those equations. It doesn't matter which one of them is which. So you only have to solve it once and it tells you both of them. See, look at this. I'll put that back in a second. I could switch lambda 3 and lambda 4 in those equations and it wouldn't make any difference. They'd be the same equations. I could have done exactly the same trick by multiplying this one by lambda 4 and I would have gotten the same equation involving lambda 4. So lambda 3 and lambda 4 you can find just from lambda 3. So you don't have to do any more. Yay! And you'll notice that when you add them together, all the complex bits will cancel out and I'll get 2. I'm not going to do the multiplication because I can't be bothered. But if you multiply all those complex number ones together, you'll get 5. Now, your lecturers who wrote your exam will be much friendlier to you than that, and everything will come out as nice, clean, whole numbers, or at least fractions, or possibly plus root 2 or something. So please don't stress with the complex numbers. But it is worth noting that if you know a complex number appears, then its conjugate is there as well. So let me give another example of that. Okay, so what if Eigenvalue 7 So A has 1, 2, 0 and 1, 1, 0 as eigenvectors with eigenvalue 7, and its trace is 2. What are the eigenvalues? Sorry, I can't find the vectors without knowing what A is. What are the eigenvalues of A? Okay, so we know that 7 is an eigenvalue because it goes with eigenvectors. And we know that there ought to be 3 because it's a length 3 vector. So if A is a matrix, it has to be a 3 by 3 matrix. So A is 3 by 3, so it has 3 eigenvectors, values. Okay? And we know that the 3 of them will add up to 2. And we know that the eigenspace for 7 has 2 linearly independent vectors in it. Okay, which means it must have dimension at least 2. Because if you whack both of them into something, it will produce at least a plane. So the eigenspace for 7 contains 1, 2, 0 and 1, 1, 0. Which are linearly independent. So the eigenspace for 7 has dimension at least 2. Okay, so the dimension is the maximum number of linearly independent vectors you can find in a subspace. So since it's got 2, it must have dimension at least 2, which means that the eigenvalue has to appear at least twice. Okay, so for every linearly independent eigenvector you find, the eigenvalue has to appear once more in the characteristic equation. It can appear more times than that, but because there might be missing ones, but it might appear another one. So it has dimension at least 2. So therefore, 7 has multiplicity at least 2. So therefore, let the other eigenvalue be lambda. And we know that lambda plus 7 plus another 7, because it's in the list twice, is 2, which means that lambda must be 2 minus 14, which is negative 12. So the eigenvalues are 7, 7, and minus 12. Okay, so what we used there was the information about multiplicity and dimension of eigenspace. But in order to use the information about dimension of eigenspace, I had to use information that I knew about how subspaces worked and how linearly independent vectors work in subspaces. For more information about that, I did do a seminar on subspaces last year, and you can look that up online, or of course you can always talk to your lecturer or in the Maths Learning Centre to talk about that as well. Right.
You knew there was only 3, so there's 2 7s, so it's
Yep.
gone straight to that equation.
But notice that someone said, I would have gone straight to that equation. Yes, but it is important to write down why. The reason why I was going straight to this equation is because 7 had multiplicity at least 2, which is because they had 2 vectors. So I wrote down all the reasons why I got to there, because then when I go back and check, so for purpose of the exam, right, you might not go back and check, but if you do this one day and 3 months later you look at it again, you may not remember why you said something, and so you need to write down why. And writing down why proves to whoever's reading what you're writing that you did it.
So it was 2 2 0 and 1 1 0, then it wouldn't have worked.
No. Someone just said if it was 2 2 0 and 1 1 0, that wouldn't have made any difference because they're just multiples of the same vector, and so it wouldn't have told me that there were 2 7s. It would only tell me that there's 1. So they have to be independent to use this trick. Cool. All right, and all that information can go through in lots of problems. I'd recommend having a look at the worked examples in my uni. I've put them on my webpage as well. They don't have videos to go with them, I apologise, because the hardware system that I was using to make them broke when I was partway through making the Eigen stuff. But there are written examples, and if you can go and have a look at how I've done them, and I've tried very hard to write explicitly what my thinking is on the page in my working, which is one of the reasons I do this. Have a look at them, and I've shown several examples of how to use scant information to find eigenvalues. Now, before I move on, does anyone have anything else to ask about eigenvalues or eigenvectors or anything at all now, before I move on from that and move on to other topics? Yes?
I want to ask a question, geometrically interpret vectors, like if they're in a plane or a line.
Yep.
How do you do that?
Okay, cool. I just reserved that for just a moment. Have anyone got any more about eigenvectors at all? Or Cayley-Hamilton or anything like that? Good, okay, I'll answer your question now. Give me a moment. I'm going to take a moment to have a glass of water, and then I'll get back to that question.